Okay, so at the end of the last video, we ended up with this low poly terrain and this camera that we can use to kind of show ourselves around a little bit, zoom in, zoom out. There's not much to this camera, but this is one chunk. It's a 1000 by 1000 vertice chunk. The terrain overall is made with noise. And today we're going to make this infinite. So we need a little character to sit right in the middle that we can move around. And just like that with editing magic, we have a bit of a better camera. So this is a cube. If we zoom in far enough, you can see that it's kind of like a UV map texture or UV checker texture. Pretty small. We don't really need it to be any bigger than this. We really care about the movement here because when we move it like that, obviously there's no other terrain generating, but we're going to make some terrain generate. And this also allows us to zoom way out and keep that moving around because we're going to use that little cube as like the location for which chunks we need to spawn. And the code for that camera controller and stuff is all in the GitHub repo. If you care about it, it is not particularly amazing. It's not the best code ever. It's not meant to be. It's just something to get us going so that we can do terrain generation. So we'll commit that. So we know for a fact that the thing that we want to do is basically spawn this terrain chunk over and over. The terrain chunk is just sitting in our main function right now. So we've got everything from our terrain height to generating this plane to modifying it with the noise, coloring it, computing the normals and whatnot. And then we spawn in this terrain. So this whole chunk of code right here needs to get repeated at some interval in some way. So what we're going to do is we're going to take this and we're going to move it to a custom command. And in our case, this is what we've ended up with. We've got this new spawn terrain struct. This struct will take an ivec2, that's a vec2 of integers. And the way we're going to use that is as a command. So commands.add spawn terrain and then the chunk location that we want to spawn. So this command then spawns each of the individual chunks that we're going to actually use in the world. That's why there's 9 of them here, because I'm doing a 3x3 sort of chunk grid, if you will. And we've also got this TerrainStore here, which is really the only additional code. So we'll talk about that in a second. But the rest of this code is all the same. We've got the terrain height, the noise. We've coded the mesh size into a variable because one of the big changes we made from the previous video now is that the positions that we use need to be adjusted by the size of the mesh because we need to get the noise from that location, not the location more close to the center. So as we move further out, we're going to take the position of the vertice in the plane mesh. We're going to adjust that by the mesh size times the chunk location. So what we end up with here is the vertice in the chunk that we're looking at getting passed in as the X and Z values here. All the rest of this code, all the colors and stuff stay the same. We still compute the normals, etc. And then because we're doing a command here, we have full world access here. So instead of using commands.spawn or whatever, we're going to use world.spawn because we can just put stuff in the world because we have, if we look back at the top, the entire world or exclusive access to the world is how to read that. So because we have exclusive access to the world, we kind of do this in a little bit of a different way than we would in a system. We can get mutable access to our resources or exclusive access to our resources using the same types that we did when it was a system. So assets mesh, assets standard material, and in this case, we're going to get the TerrainStore, which we haven't talked about yet. We know these are always going to exist, so we expect on them. And then this gives us the same thing as usual. So if you were going to write meshes.add some mesh or materials.add some material, that's what these are. We're just getting the resources directly from the world and adding them immediately. So this gives us a handle to our mesh and a handle to our standard material. Same stuff we had before. Then what we do here is we spawn it. So we have our handle to our mesh, handle to our material, and we need again to add this mesh size adjustment times the chunk. So we're in some chunk with an X and a Y coordinate, and we need to multiply that by the mesh size to put it in the right position. So all of that together looks like this, and it's a little hard to tell when it's all looking perfect like this, but this is 9 different planes, which we can prove by say, let's take out the middle and let's take out maybe this one. So now we're only going to spawn 7 of them. I'll make this full screen and we'll zoom out, and then the middle one is missing and the right-hand side one is missing. So we're good to go here. Now, this is not yet actually spawning any infinite terrain. We've just set up the ability to actually call this command to generate the terrain, to generate the mesh and spawn it as often as we want to. The one other thing we've done is this TerrainStore. So this TerrainStore is a hash map from a chunk position to a mesh handle. Now I did it like this specifically because it is possible that you have, mesh handles somewhere else, use them for something else, store them in some other way. So we're going to key off the chunk position, so 0, 0, 1, 0, etc. And we'll store these handles right here. So world, get resource, TerrainStore. We expect to be able to get that. We get the hash map inside of it. And then we're inserting the chunk position alongside a strong clone of the handle, which will just keep this around for us. So these meshes aren't going to go away just because we despawned it or something like that. And right up at the top of our command, we also get the TerrainStore. We go into the hash map and we check to see if that chunk has already been generated and the handle is stored in the TerrainStore right now. If it is already in the TerrainStore, we don't want to do all the costly generation, so we're just going to return because the mesh already exists. And in this case, I've tied the mesh existing in the TerrainStore to already being spawned. But you don't technically have to do that. You could disconnect them in whatever way you wanted to. For example, if the mesh generation was extremely costly in CPU time, but not very costly in RAM, like you were running some kind of maybe erosion simulation or something like that, then you might want to store the handles to these meshes in memory for longer, even if they're still spawned. So we're going to use this TerrainStore as we move forward here to allow us to basically add these spawn terrain commands for the 3x3 block of chunks that we want to actually spawn. And for the vast majority of these, for 6 of them approximately, they won't have to do any work, and then we'll just spawn 3 of them because we'll be moving, say, forward, and 3 of them will disappear, 3 of them will get generated. So we'll commit this again. So we have the command refactor here. And then the next thing we're going to do is write a system to manage the chunks. This system is running an update, so it runs once a frame. And the purpose of this system is to figure out which chunks should be rendering right now. If we run this, and maybe I zoom out a little bit so you can see it, you can see everything kind of jump there for a second. And that's because we keep generating. I guess we're going the wrong way. I guess we're going backwards. I meant to go forwards. So you can see which direction the cube is going here. And actually, it's very obvious if we sort of zoom in a little bit, but the whole application kind of hitches when we do that generation. So if I zoom out and start talking through it, and then I make sure that I keep talking, you can see that it hitched, even though all of the stuff is getting generated when we move off the map and it's getting removed. And you'll see we have a bunch of logs here. In this case, it's mesh 0, -4 already exists because we, again, are doing that kind of like caching. So manage chunks is going to use a local, which is an IVAC2. So it's going to store the current chunk in an IVAC2, which is going to default to 0, 0. That just so happens to be where we're also spawning. But you could easily store this in a resource instead of a local. Locals are just system local state, effectively. And then we've got the ship, which is that little cube that we built and spawned into the world. So depending on where the cube is, we're going to determine which chunk we're in, and thus which chunks to spawn. We've got our terrain store like we talked about earlier, and we're also querying for all of the terrain entities. That's any entity with a mesh handle that has the terrain component on it. The terrain component is not interesting. It's a unit struct, so there's no data attached to it. It's just labeling all of our meshes, or all of our entities that have our meshes. So given the chunk size of 1,000, which is the same size as our meshes, if you look up mesh size 1000. So when we do our plane, it's .mesh.size 1000 by 1000 with 200 subdivisions. We have this chunk size. We get our ship, or specifically the transform of our ship, and then we start doing some interesting things with that. We take the translation of the ship, so it's XZ position. Remember, Bevy is Y up, so XZ is the horizontal plane in which the ship is moving. We're dividing that by the chunk size to get a chunk value. So this will give us like 0, 0, or in this case, it could also be like 1.5 or something like that. But that's also why we use trunk. So if we go to glam vec2, which is the same thing as bevy vec2, and we go to trunk, this returns a vector containing the integer part of each element of self. This means numbers are always truncated towards 0. This is the behavior we want. It's important that we have that behavior because chunks can be either on the positive axis or the negative axis. So if you are in chunk 1, 1 and -1, 1, we want those behaviors to be the same. We don't want to floor it because flooring would take it in the wrong direction in one of those cases. So we truncate. We just drop that additional amount. And then we're turning that into an IVEC2. So we get an XZ coordinate for which chunk we're in just by doing a very small bit of math. If the chunk we've calculated is not equal to the current chunk, so in this case, when we start for the first time, it's 0, 0, and this could be anything. If they aren't equal, then we've moved into a different chunk. We set the current chunk to that XZ chunk, whatever that is. If we were in 0, 0, maybe we went to 1, 0, maybe we went to 0, -1, maybe we went to one of the other options. We then define which chunks we want to render based on the current chunk that we're in. This is going to be the current chunk position, so it could be 0, 0, let's say. And then this would be chunk -1, 1, and -1, 0, and -1, 1, and 0, -1, etc. If this current chunk was 1, 1, then this would end up being 0, 0, and so on and so forth. So we get this 3x3 grid. We're just doing some very small IVEC2 creation and addition here to get those positions. So we've got a number of chunks that we want to render, but remember the TerrainStore is where we are keeping track of which chunks are rendered. So while there is a really perfect function for this, there's extract if. The only issue with extract if is it's on nightly. Does seem like this is pretty stable at this point. This does exactly what we want, but we aren't going to use it because it's a nightly API. I would suggest if you're comfortable with nightly, definitely go use this. What this does is it basically applies a test to every element in the hash map, and the ones that pass the test get taken out of the map, and the ones that fail the test get kept in the map. That would be really useful for us here because remember, this is a hash map of chunk positions, and we've got a list of all of the chunks we want to render. So if the chunk positions inside of TerrainStore don't match the ones here, then we need to drop them. And that would be exactly what extract if would do for us. Since we don't have that, we're going to iterate over that TerrainStore hash map. We're going to filter for anything that doesn't include a chunk that we want to render. So this key is an IVEC2. We're checking the chunks to render array to see if that key is in there. If it's not, we want it. And then we get chunks to despawn as an IVEC2 and a handle to a mesh. Now we are cloning this entirely, but remember we only have 9 items, so this isn't really an issue for us. Also, IVEC2s are effectively the cost of 2 integers, and a handle to a mesh isn't like an ID. So these are not costly clones either. So we take the chunks that we should despawn, if we can find them into the terrain entities query, by checking to see if the handles are the same. So if the handle from the terrain entity matches the handle from the chunk we want to despawn, then we can actually despawn it and also remove it from this TerrainStore. So the handle to the mesh will be gone at the end of this. Otherwise, we just continue this loop. And then finally, we do a very brute force for every chunk that we want to render. We add a command to render that chunk. This is our spawn terrain that we did earlier. And with that, we get infinitely spawning terrain. Of course, remember there's this issue where if we get too close to the edge and it needs to do the generation, it's pretty slow. Now, the question is, why is it slow like that? And there could be a number of reasons. We're going to cargo run in release mode here. And I'm going to show you that actually in release mode, this doesn't even flinch at all. This is no issues in release mode, which means it's just an optimization problem. There's no issue with our algorithm. There's no issue with our implementation. This is quite literally just an issue with how much optimization we're letting the Rust compiler do on our actual code. But you don't want to run in release mode all the time. So in our cargo toml, we're going to enable optimizations at a fairly high level for Bevy and other packages, things that don't get recompiled very often. And then we're going to enable a small level of optimization for our code. And now if we run in debug mode with those optimizations set in our cargo toml, then we have no issues at all. This is fully performant just as if we had run cargo run release, but we still have access to all the debug symbols and whatever else we would want. And if I clear this and we take a little bit of a closer eye at these logs, then we can see this generate. Maybe I'll move this over here so we can see it a little better. You can see that 6 of the planes or 6 of the meshes already existed in our TerrainStore, so we didn't need to regenerate those handles. If we keep going, it'll happen again. It'll go for another 6 of them because that happens to be the direction and the way that we're moving. So roughly speaking, because we're doing a 3x3 chunk generation, 6 of those are already cached and ready to go, and 3 of those are just being regenerated on the fly whenever we move around. And that ends up with this behavior where it looks like it's going and then it chunks forward a little bit, but the back 6 are always getting, kept, and the future 3 are always getting regenerated. And that gives us just infinite terrain to, fly through or whatever. Obviously, you would want to change some of these values if you were doing this for real. This is, infinite terrain generation technically, but maybe you want, 4x4 or something like that, some different chunk size, something that suits your application better, etc. But that all works. So that's infinite terrain generation, low poly. I haven't really shown the meshes at all, but these are all the meshes. Again, because we're doing the meshes on the items that have already spawned, you can see if we've spawned in a new plane that there's actually a cutoff here. So this is exactly the seam or where the seam would be. And we can kind of look at both sides here and see what's happening. But this seam is almost imperceptible because we are using that noise, and that noise is exactly the same value for both of these. So you can see that this vertex in particular stays in almost exactly the same spot, which is great. So that's infinite terrain generation. I think a future video will cover asyncifying this terrain generation. We'll try to make it maybe a little bit more intense. And then maybe when we get to it at some point in the future, we'll actually take it from async and maybe try to do it on the GPU. But I'll leave that for later. So if you have any questions, leave them in the comments. Code is linked to in the description, and I will catch you in the next video. Have a great rest of your day.